Hi there, Physics 121 students. My name is Neil, and my project is something called the piezoelectric transducer. So let's get started. So, what is the piezoelectric crystal? Essentially, it's a special type of crystalline structure that allows the formation of electric fields to be generated within molecules. So, let's try to understand exactly how this works. So, on the image on the left, I have taken a small snapshot of a small bit of the crystalline structure. And essentially, you can see that we have natural electronegativities that exist within the crystalline structure. And you can see that we have a center of charge. So each positive and negative pair tend to cancel each other out. And essentially, the molecule is neutral. But the thing that's special about these crystalline structures is that they could physically be manipulated. So they physically conform and change their shape with physical pressure. So in the middle picture, we have a picture of a compressive force that changes the structure. And essentially, now you don't have a neutral charge anymore. Instead, you have a positive and negative um, charge, which induces an electric field. And just imagine this effect, but for all the molecules on the right, in the image on the right, you see all these molecules each generating their own electric field when the entire crystalline structure is under the compressive force. So essentially what it does is that when you push or you apply mechanical pressure to the crystalline structure, you generate all these electric fields. And one thing we know is that voltage is just the integral of the electric field. So I actually managed to synthesize the crystals at home, and it's a pretty simple process. So let's go over how it works. So the first thing I had was I had some baking soda, but I needed the baking soda to be washing soda. So on step one here, I have Na8CO3. I basically heated it up and it gives me the washing soda, which is Na2CO3, plus some byproducts of carbon dioxide and water. So at the bottom left in picture, step one, you can see I have the baking soda in an oven, and I basically just heated it up. And after a few hours of it being in the oven at, I believe, 250 degrees for a few hours, it's quite high, but at the end of those 2, 3 hours, I was able to get washing soda, which is the chemical formula of Na2CO3. Then, so that's my step one, just heating up the soda, which gives me the washing soda. Then the second step is mixing the washing soda with something called cream of tartar. And once I mix the cream of tartar with the washing soda, I essentially mixed it in a Pyrex glass and I put in a body of water just for it to heat up quicker. And so after heating it, I just essentially mix the washing soda and cream of tartar together. And I just essentially continuously stir it until the solution becomes clear, transparent rather. And then once the solutions become transparent, I actually poured it into a container, as you can see on the extreme right. And the remaining solution is actually something called potassium sodium tartrate, and that's also known as Rochelle salt, which is a double salt of tartaric acid. So essentially, potassium sodium tartrate is the final product, and also the Rochelle salt slash the piezoelectric crystal in this case. Another interesting effect about the piezoelectric crystal is something called the piezoelectric law. So essentially, the piezoelectric effect is just a complex way to say that a pressure on the crystalline structure will generate an electric voltage. So using Gauss's law, we know that the integral of the electric field is equal to Q inclusive over epsilon naught, but this is derived to another equation which gives us the voltage. So voltage is equal to um, the piezoelectric coefficient multiplied by the force multiplied by the thickness divided by some constants multiplied by the area. So essentially the voltage is proportional to the force that we apply, and that's the main thing that I want to kind of take away from here. So essentially the more force we put onto the crystal, the higher voltage we get. And that makes sense because the more force we put on the physical crystalline structure, the more distant those charges inside each molecule get, and that induces a more stronger electric field, which in turn produces a bigger voltage. The next step is learning what a transducer is. So, a transducer is basically any electronic device that converts energy from one form to another. So, the way that I explore this in my project is converting the mechanical energy of the force to something like an electrical impulse. So, the way I do this is I have my piezoelectric crystal set up on the way. So, on the image I have, you see something called the direct piezoelectric effect and the converse piezoelectric effect. So the way I have my circuit set up is something similar to the direct piezoelectric effect, where I have a crystal and I apply force to the crystal and I'm able to get some voltage out of that. So that's why I call the project the piezoelectric transducer, because basically the crystals are just a method for you to convert your mechanical force into electrical impulses.
Hi there, Physics 121 students. I'm here to demonstrate my piezoelectric crystal in action. So let's take a look at how it works. So right now, I have my piezoelectric crystal set up, and it's actually wrapped around inside a foil, and I have it hooked up to an oscilloscope. So the first thing that I have it on is, as you can see, I don't have much noise. It's pretty distant, but when I try to attempt to take a sample, let's see how it takes a look. So I'm just pounding the pencil. I'm giving mechanical pressure to the crystal, and you can see that there's a little bit of noise, but you can definitely see some voltage fluctuations over time. So, as you can see clearly from before, we had this noise, and from before, if you take a look back, some of the noise, as I was pounding the crystal, there was voltage fluctuations from all over the graph, and essentially this graph is a function of voltage over time. So the y-axis represents the voltage, x-axis represents seconds. And the oscilloscope is a pretty cool equipment because it allows me to take sensitive measurements. So on the time axis, my units right now are 5 milliseconds, so every block represents 5 milliseconds, and in the y-axis, every block represents 50 millivolts. So every time I attempt to take a sample, you can take a look. So yet again, you see me pounding, applying mechanical pressure to the crystal, and you can definitely see there's voltage fluctuations coming out of this crystal. And despite it being small, there is a small electric potential that's being generated due to the mechanical pressure of this crystal. So yeah, that's pretty cool. So, after conclusive findings, I find that the oscilloscope is much better suited for finding the small AC voltage coming generated out of this crystal. And initially, I had a multimeter set up for trying to find this, but there was too much apparent noise, and it was pretty hard to determine how much voltage was being generated by the crystal. So, this oscilloscope gives us a better idea of how much energy is generated. And let's take a look. So, inside the foil right now, I don't want to open the sample that I have right now. But if I was to open some of the thing that I have, it doesn't look too pretty, but I have some of the crystalline structures settling on the foil right there, as you can see. And essentially, once I wrap this foil up and I give it some mechanical pressure, it gives me the energy generated and shows up on the oscilloscope. So yeah, that's pretty cool. Another example I have of taking measurements is using the digital multimeter I got over here. So right now, there's no way for me to isolate the noise that's being generated by the environment I am in right now. So I'm gonna just try to show the basic readings it's coming out to. And as you can see, it's coming out to basically in the decimals, all the readings. So if I were to apply a small, so let's attempt at connecting the electrodes in the solution. And as you can see, if I was to give it a small nudge, so all I'm doing is I'm pushing the crystals and generating that mechanical energy. As you can see, it generates a small current around, well, it varies every time with the force I put, and it varies according to the equation that I showed from before. But yeah, you can see it generates a small current. This is in DC. And yeah, it's a pretty small current coming out to an average of around 20 millivolts, maybe 20. It really varies. It depends. So if I put a lot of force, it comes out super high. And if I put in less force, like really small numbers. So yeah, we learned that the force is proportional to the voltage generated in this case. Although, the one thing that is for sure is that I can't take for certain the noise coming out of this reading. It could be such that when I apply pressure to the crystal, there's more noise being generated, and that's why I'm not going to be using the results generated from the multimeter for my experiment, but rather I'll be using the oscilloscope measurements, because I just think it's a better measurement of voltage over time compared to this, because essentially the multimeter takes the current, the voltage as an average. Meanwhile, the oscilloscope gives me the instantaneous voltage in the form of a sine curve. So yeah, that's my experiment. So I have some of it wrapped inside there, and this is just an example to show you how this solution, crystalline solution, actually looks like.